Hey LearningHub fam, ever wondered why your computer can juggle so many tasks without turning into a digital sloth? Today, we're unlocking the secrets of cache memory. But first, a brain tickler. What's faster, finding a book on your messy desk or grabbing the one you were just reading? The answer, my friends, is the key to understanding cache. Welcome back to LearningHub, where we make tech easy and fun. Imagine your CPU as a super fast chef and your main memory as a pantry. The chef needs ingredients fast to cook up your programs, but the pantry is a bit of a walk away. That's where cache comes in. It's a small, super speedy storage area right next to the chef, holding the ingredients he uses most often. But why not just make the pantry or RAM super fast too? Well, speed costs money. Cache memory is made of faster, more expensive technology than RAM. So, we use a smaller amount of it strategically. The magic of cache relies on something called locality of reference. This basically means that programs tend to access the same data or instruction over again and again, which is also called temporal locality, and also accesses data that's located near each other in the memory, which is also referred to as spatial locality. It's like how you usually reread the same lines of a book or you keep on reading from left to right of the same page. We'll break it down. First of all, temporal locality. If you access a piece of data, you're likely to access it again soon. Think of repeatedly using the same variable in a loop. Next, we move on to spatial locality. If you access a piece of data, you're likely to access data nearby in memory soon. Imagine accessing elements in an array one after the other. This is because of the code structure that we make. Now, how do we know if our cache is doing a good job? We use two metrics, hit ratio and miss ratio. The hit ratio is the percentage of times the CPU finds the data it needs in the cache. A high hit ratio is what we want. Miss ratio, on the other hand, is the percentage of times the CPU doesn't find the data in the cache and has to go all the way to RAM. Example, if the CPU asks for data 100 times and find it in the cache 90 times, the hit ratio is 90% and the miss ratio is 10%. The higher the hit ratio, the faster your computer runs. Okay, so we know the cache stores frequently use data, but how does the CPU know where in the cache to look for it? That's where cache mapping comes in. There are three main types: direct mapping, associative mapping, and set-associative mapping. With direct mapping, each memory block has a specific location or line in the cache where it can be stored. It's like having assigned parking spots. Your car always parks in the same spot. But the problem here, if too frequently used memory blocks happen to map to the same cache line, we get a lot of collisions and the cache becomes less effective. To determine which block of the main memory resides in the cache memory, we use the following formula: I equals J mod M, where I is the cache line number, J is the main memory block number, and M is the number of lines in the memory. Next, associative mapping. It is more flexible. Any memory block can be stored in any available lines in the cache. It's like a free-for-all parking lot. This avoids collision and maximizes the use of cache. But the CPU has to search the entire cache to find the data, which can be slower. Think of it like this: you lose a book in your house. In the direct mapping, you know the exact position of where the book is supposed to be in your house. But in associative mapping, you'll have to search for the entire house to find your book. The third one is the set-associative mapping. It is the best of both worlds. It divides the cache into sets, and each set contains multiple lines. A memory block can be stored in any line within its assigned set. It's like having assigned parking zones, but within your zone, you can park in any available spot. This reduces collision and limits the search area, providing a good balance of speed and efficiency. So, what happens when the cache is full and we need to bring in some new data? We need some replacement policies here. Now, we'll talk about how we write data into the cache. There are two main strategies. First one is write through, where every write to the cache is simultaneously written to the main memory too. This ensures data consistency, but it can be slower. The second approach is write back, where writes are only made to the cache. The data in the cache is marked as dirty. When the block is replaced, the dirty data is written back to the main memory. This is faster but more complex to manage. Imagine writing a note. With write through, you write it on both a sticky note or a cache and directly into your note or a main memory at the same time. With write back, you only write it in the sticky note and then transfer it to the notebook later when you need the sticky note for something else. So there you have it, cache memory, the unsung hero of computer performance. It uses locality of reference and clever mapping strategies to keep your CPU happy and your programs running smoothly. I hope you enjoyed learning about interesting mapping algorithms and writing policies related to caches. So don't forget to like, subscribe and hit that notification bell for more tech-tastic content from LearningHub. And leave a comment below telling us what's your favorite tech hack to speed up your computer. Until next time, stay curious and happy learning.